Okay, so energy transfers. The first thing in energy transfers that you guys need to know is energy transfer diagrams. So here, it's got a few characteristics. We've got an input energy, an arrow, some kind of mechanism that we put in a box, another arrow, and then an output energy. So let's do a few examples. Example, winding up a clockwork car. So as we are winding it up, we are using kinetic energy. So we have kinetic energy, which then gets transferred via some gears inside the clockwork mechanism to potential energy. Technically, this is the elastic potential energy. But in your books, this is called strain energy. Okay, so our kinetic energy gets turned into some kind of potential energy. So here, letting a clockwork car run. So here we have the strain energy becomes, via some gears, kinetic energy. Okay, so running a battery-powered car. So here we've got slightly more going on than just the clockwork sort of car that we had there. So first we have a battery. So our battery starts with chemical energy, which then becomes electrical energy. Which then becomes, via an electrical motor, kinetic energy. So you can see they can have multiple steps, not just one step, like here. But then we get to Sankey diagrams, which, quite similarly to these, describe how energy is busy being worked with, but there's a key difference. Here it does not have a mechanism. There is no little box that tells us how the energy is being changed, like over here with a motor. Here we've got some amount of starting energy, and then we've got some amount of output energy, which is a straight arrow. These are the kinds of energies we want. And then we've got some wasted energy or energy transferred to something else, which we don't want, which is an arrow coming off of the side. And these are normally proportional. So these two added together gives us the amount of starting energy. So here's a few examples. So draw Sankey diagrams for different kinds of light bulbs. So these are actual numbers that I got for these light bulbs. So an incandescent bulb is that kind of bulb that has the wire filament inside it. So only 5% of the energy of an incandescent bulb is actually converted to light. I saw a spelling mistake, sorry. So if we go draw one for an incandescent bulb, then we have our amount of starting energy. So this will be our electrical energy. And this is then going to get turned into two different kinds. So here we've got our output energy, which is light energy that we want. And that is our output over there. But 95% of it gets wasted over here. And that would be wasted heat energy, or just heat energy. Okay, so this is for the incandescent bulb. Then we've got our fluorescent bulb. Those are the ones that have that little glass tube with gas in it. 85% of the energy in a fluorescent bulb is converted to light. The rest of it is converted to heat. So if we look at a fluorescent bulb, then they look slightly different. We've got over here our input energy. Then we have our output energy over here, but that is 85%. So that looks slightly different. Just erase this so we can do that properly. Like a pen, please. Thank you. So that would be our light energy that comes out. And this over here is then our wasted energy, which is heat. So fluorescent bulb. So here we have electrical energy. This is our wasted energy. And here we have our light energy that we want. And then our last kind of bulb here is an LED bulb, where 90% of the energy is converted to light. So it's going to look fairly similar to this one, except we're going to have an even smaller output arrow over here. So there we've got our output energy that we want. And over here, very tiny arrow, that would be our wasted energy. So this is the LED. I'm not going to fill it in completely because it looks pretty much the same as those. So this is a diagram from your textbooks, which talks about the parts of a power station. So here we have a coal, oil, or gas furnace, or a nuclear reactor, which is then used to heat up the water to turn it into high pressure steam. The high pressure steam then goes on to turbines, which makes them turn. The turbines turns an electromagnet inside a coil, which turns the magnetic energy into electrical energy, which you can then use via transformers to actually go to where it's supposed to be needed. So this is a very sort of complex system. So let's first walk through the energy transfers that's happening here. So here we have chemical energy in our coal, oil, or gas. Which becomes heat energy. The heat energy gets transferred into our steam. So it doesn't change the kind of energy, it just changes which material carries it. So our steam then gets pushed into over here onto the turbines, making them turn. So here we have heat. So here we've got heat energy. Here our steam is moving. So here it's turned into kinetic energy. Here it turns these, which turns it into some more different kinds of kinetic energy. This turns an electromagnet. So now it's this electric energy or kinetic energy is turned into magnetic energy. The magnetic energy rotates in a coil, which turns it into electric energy. Okay, so here we've got magnetic energy, and here, finally, out the end, we've got electric. So this is remarkably complicated. So now we're going to draw an energy transfer diagram and a Sankey diagram for a power station. Bear with me. Okay, so first, energy transfer diagram. We've got chemical energy. I'm not going to write out energy each time. I'm just going to replace it with a big E to save space. So we've got chemical energy, which via the boiler gets turned into kinetic energy for the steam. The kinetic energy of the steam goes through the turbine to turn it into a different kinetic energy. This kinetic energy then goes into the electromagnet So this becomes magnetic energy. So here we've got the electromagnet. Oi, that's not enough space. And this gets turned into magnetic energy. The magnetic energy rotates in a coil, which turns it into electric energy. Rather complicated process over here. So now if we want to draw a Sankey diagram, we need to take into account that we've got wasted energy at all of these sort of points. So let's start with 90% of the heat of the coal is actually transferred to the water or steam. The rest is lost to the atmosphere as hot gases. So let's start there. So let's start with a rather big start over here. So here we've got the chemical energy from the coal. So 90% of this, so that would be that much, goes on. So here we've got it as heat energy in the steam. And here we've got a waste product coming out. And this over here is heat energy, which goes into the atmosphere. Okay. So of this part here, 43% of the energy of the steam is transferred to the turbine. Okay, so let's first divide that up. Here we have slightly less than half, so there's our 43%. So this goes towards the turbine. So here we've got kinetic energy. This is our turbine. Okay, the rest is either lost in the cooling process or 60% of the heated water is added back as water to the boiler. So here, of this part, 60% of it, so that would be about slightly more than half, gets added back to the boiler to be used again. So this is reused hot water. Okay, and here we have this part coming out, and this is our wasted energy. From this process over here. So that was just at the turbine. So now the energy from the turbine, 90% of it gets turned into electrical energy and the rest is lost due to friction. So here we've got 90% of it, which is about that much. This is our actual output that we want. So we've got electrical energy. And here we've got this bit that gets lost, and this is due to friction. So this is a rather complicated Sankey diagram. This reused hot water, we didn't have to curl back into here. We could have just had an arrow ending over here. So these numbers are also actual numbers that I got from the power stations, from Eskom's website and so forth. So the only number that I'm not sure about is that one there. The 90% of the energy in the turbine gets turned into electrical energy. But in the end, throughout the whole process, a third of the energy that goes in via the coal actually comes out as electrical energy. So if we look at this area here and this bit here, this is supposed to be about a third of this whole area here. So it's more or less right. Okay, so what this tells us is that our boilers and our power plants are not remarkably efficient. So that is the technical bits that you guys need to know how to do. So you guys need to be able to draw energy transfer diagrams. That's the ones with the boxes that shows you the mechanism of how it gets transferred. And you guys need to be able to draw Sankey diagrams. You will probably not get a diagram as complicated as the power station one that I drew. So now we are going to be looking at some lovely simulations and things from the PHET labs at Colorado University. So I want that one. Thank you. Okay. So I hope you guys can see this. Let me know in the chat if you can't, but let's start. So here we've got energy forms and changes. So there's a little introductory part and then there's some systems. So let's go look at the introductory part. So here we've got some heat and we've got water and oil and iron and brick. So the idea is just here to be able to show, so we can add a little thermometer there. And there we've got a brick. And we can add a little thermometer there. So so now you can see the energy that is already contained in them. If we add heat, that adds some more energy to these. And then we can eventually see which one gets hotter and so forth. And then it can start actually letting go of the energy. So now if we look at energy systems, here we've got some kind of input. Here we can select our input. There is a pipe with some water that it can let go. There is some sunlight that lets out some sunlight energy. There is a kettle that lets out some steam, and there is a bicycle which uses chemical energy from the food the person ate that gets turned into some kind of kinetic energy. Okay, so here we've got two different ways of using this energy. We've got something that turns, and then we have a solar panel. And here we've got some kind of output. So here we've got a coil heating up some water, and then we can see how hot it gets. Here we've got a light bulb to see, here's a different kind of light bulb, and this is a fan. So let's start with our basic setup. I'm going to turn the energy symbols on. So here you can see that water already has some stored heat energy. Everything has some stored heat energy in it. So as I turn on the water coming through, you can see we've got some kinetic energy of the water. Here, the kinetic energy gets transferred to this bit as it is turning, and then behind this there's probably a turbine hole sort of thing that turns it into electrical energy. The electrical energy goes into the coil, which gets turns it into heat energy, which gets transferred to the water, making it boil. We can replace the water with a light bulb, and then you can see the electrical energy reaches there. It gets turned into heat energy, which is the red ones, and light energy, which is the yellow ones. You can see here we get a lot more heat than we actually end up getting light in the beginning. So here we can end up with, So here we've got a fluorescent bulb. So we've got electrical energy becoming heat energy and light energy. And a fan, we've got electrical energy becoming kinetic energy spinning the fan, which then becomes kinetic energy by moving the air around. So let's go look at a solar panel. So here we've got a solar panel, the sun that is pushing out lots of light particles. As it hits our solar panel, it can either bounce off, as that one did, or it can be turned into electrical energy, which can then be added to water or to the light bulb, etc. Okay, so this is a lovely thing to go play around with the changes in energy. It is phet.colorado.edu. They have lots of simulations and things. They bounce off just due to the fact that the solar panel is slightly reflective. So solar panels don't work 100% efficiently. Some of the sun's light that actually reaches them gets bounced off due to the fact that it reflects. Okay, so that's the simulation. Now I'm going to show you guys this one. So this is the pendulum lab that they have. You can also find them, same website. They've got lots of simulations that you can play with. So here we have a pendulum, and it's a kilogram, and that, so now we can start by swinging it, and now we have some gravity. There's earth gravity, and we can see that it's busy swinging. And that's about it that the intro bit can show us. We can add in another pendulum that is slightly longer, and then we can see what happens. So if we add friction, you will see that it starts slowing down and going lower until eventually, after quite a long while, it's going to stop in the middle. Okay, so now let's look at our energy over here. So if you look at this graph, that is kinetic energy, that is gravitational potential energy, that is thermal energy, and that is our total amount of energy. So if I start by starting it off over here, you will see that my potential energy is very high, because here it's got, gravity has the biggest pull on this weight. So as I start swinging it, I'm going to slow it down. You will see as it reaches this point here, it has the greatest amount of kinetic energy. So here, there, all of its kinetic energy, and now everything is going back to potential energy. So as the pendulum swings, it switches in between those two, the kinetic energy and the potential energy. But our total energy that this system has stays the same. So now, if I go and I add some friction, so friction happens because things move against each other. So at the point where it has the most kinetic energy, it will start turning some of that kinetic energy into thermal energy due to the friction. So that is what's happening here. So over here, these won't reach as high, and every single time we will get some more thermal energy being made. And that is how it eventually slows down and stops right in the middle. So it'll stop once all of its kinetic energy that it can have has been turned into thermal energy. Okay, so over here, we've got our same energy graph. Now we can add velocity and acceleration vectors so that you can see what happens over here. So here we go. Let's just start it swinging. I'm going to make it slow again. Here you can see its velocity is at its maximum point once it's down here. And there, the velocity is increasing again, and there we go. Okay. So if we add friction, our velocity is still at its max, but it turns some of it into kinetic energy, thermal energy, and so it doesn't swing quite as high. So another great thing to go play around with energy transfers. Then there's one more I want to show you guys. So let me just share that one. If I can find it. There we go. So it has this website, phet.colorado.edu, has both the web-based simulations, and then it has simulations that you can download that runs in Java. So here we've got a skater, and he's going to start skating. So there we go. And it'll pretty much reach the same sort of height that he had as he started. So we can show a pie graph over here, which shows you the green is the kinetic energy and the blue is the potential energy, how it gets converted as he is busy traveling. So in this simulation, you can go play around with heights and things. So this is our potential energy 0 over there. So we can start him out by going really, really quickly over there. We can add some more tracks. So here we want him to go into a bit of a loop. So let's do that. Add another track. There we have a lovely loop-de-loop coming out. And here we just want to have a nice big tall distance so that he can not fly off into space. So let's see what happens. So here he's going. You could see over there, he still had some of his kinetic energy left, and that is why he could go round. So that's how that works. That's how roller coasters work. Since they still have some kinetic energy pushing them upwards, they can go around the loop easily. So here we can play around with lots of different things. There's a measuring tape that you can use. You can choose different skaters of different kilograms. There's a bulldog that only weighs 20 kilograms. There he goes. Great. You can show the path that they are traveling. So here you can see it's literally like ticker tape. The further away the dots are, the faster they are traveling. So we can show that was the show path. Where is the show path? There we go. Okay, you can show the energy versus position graph over here. So here you can see there he goes around the loop and back. So there are lots of things to play around with in these to do with energy changes. You can also draw energy versus time graphs. So the yellow is our total amount of energy. The green and the blue are our kinetic energy and so forth. We can add friction. So let's add some friction to this. So now you can see the red, which is our thermal energy, starts increasing, and then he will start slowing down. Okay, so those are the things I wanted to show you guys. And the website is phet.colorado.edu, where you can get all of these simulations. And their simulations are free to use for any educational purposes.